One formula decides if a discovery is Nobel Prize worthy or an embarrassing mistake. In 2014, scientists announced they'd found echoes of the Big Bang. Headlines were everywhere. And then they retracted. 2 years later, different scientists announced gravitational waves. Same statistical standard. And they won the Nobel Prize. The difference? One team seemingly understood their noise, and the other one didn't. Today I'll show you the exact formula and the statistics you need to actually use it correctly. First, let's understand what sigma actually means. Sigma, this Greek letter, is the standard deviation. It measures how spread out your noise is. Small sigma means your measurements cluster tightly and your noise is predictable. And large sigma means your measurements are all over the place. The noise is wild. And here is why this matters. If your noise is small, even a small signal stands out. If your noise is large, you need a much bigger signal to be confident it's real. Here's the formula. It looks scary, but it's just 3 steps. 1. Find the mean, the average of all your values. 2. For each value, calculate how far it is from the mean, and then square it. 3. Average those squared distances, then take the square root. And that's sigma. It tells you the typical size of a random fluctuation in your data. Now this is where sigma becomes so powerful. Once you know your noise level, you can ask the key question. Is my signal real or just a random fluctuation? Signal to noise ratio, or SNR. Take your signal, that's just what you measured minus the background. Divide by sigma. The result tells you how many sigmas above the noise is your detection. If it's 1 sigma above, that's probably just noise. If it's 5 sigma above, that's almost certainly real. Now, here's where most explanations get a bit confusing. So you've probably heard the 68, 95, 99.7 rule. 68% of data falls within 1 sigma of the mean, 95% within 2 sigma, and 99.7 within 3 sigma. But this is about the distribution, how data spreads around the mean. It's not the same as detection significance. When we detect something, we are asking a one-sided question. Is this signal above the noise? Not different, but above. Because a galaxy can't be negatively bright. We only care about positive detections. So the correct numbers for detection are 3 sigma, 0.13 chance of false positive. That's 1 in 740. And 5 sigma, that's 0.00003% chance. That's 1 in 3.5 million. These are one-tailed statistics. For detection, this is what matters. So, what thresholds do scientists use? 3 sigma is evidence. Something interesting is probably there. One-tailed, there's only a 0.13 chance, 1 in 740, that noise fooled you. 5 sigma is discovery. You can probably publish, you can win a Nobel Prize. In one-tailed, 1 in 3.5 million chance of false positive. This is why particle physicists need 5 sigma to announce the Higgs boson. This is the standard LIGO used for gravitational waves. But here is the important lesson. Your significance is only as good as your sigma. March 17, 2014. The BICEP 2 team announces a discovery. They claim greater than 5 sigma detection of primordial gravitational waves. B-mode polarization in the cosmic microwave background, evidence of cosmic inflation, Nobel Prize territory. The problem, their sigma was wrong. They estimated their noise using a preliminary dust map from a Planck satellite presentation slide. And when Planck released proper data, it showed far more galactic dust than expected. That dust created polarized light, exactly mimicking their signal. Their real sigma was much higher than they thought. Their 5 sigma detection wasn't. And then they retracted. Now contrast that with LIGO. September 14, 2015. 2 detectors 3,000 kilometers apart. Hanford, Washington and Livingston, Louisiana. Both see the same signal 7 milliseconds apart. Exactly the light travel time between them. A chirp. 2 black holes. 36 and 29 solar masses spiraling into each other. 1.3 billion light years away. Combined false alarm rate less than 1 in 203,000 years. That's approximately 5.1 sigma. But here's what made it bulletproof. They spent years characterizing every source of noise, seismic vibrations, thermal fluctuations, and even trucks driving by. They also did blind injection tests. Those are fake signals inserted secretly, which the team had to detect correctly before any real claim could be trusted. Their sigma was accurate. Their noise model was real. And in February 2016, there was a public announcement. October 2017, they won Nobel Prize. So how can you use this? Let me show you. This image is from my Seestar S50. There is something faint here, but is it real? So let's go through the steps. Step 1. Measure the background noise. I sample 500 pixels from empty sky. The mean and the sigma is here. Step 2. I measure the target. The peak brightness is calculated here. And step 3. I calculate the SNR. So the signal minus 1024, 111 counts. SNR equals 2.36 sigma. That's below 3 sigma. With one-tailed statistics, there is about a 1% chance this is just noise. Evidence? Maybe. Discovery? Well, not yet. I need more data, more exposure time, stack more images, but now I know where I stand. I am not guessing. And what's the real lesson here? It's not just about getting 5 sigma. It's about getting the sigma right. Bicep 2 had 5 sigma, but the wrong sigma and retracted. LIGO had 5 sigma, right sigma, and they won the Nobel Prize. A detection is only as real as your noise model. Measure your background carefully, understand your noise. Then, and only then, can you trust your sigma. So here it is. That's the formula. Signal divided by sigma. It's the same math that proved the Higgs boson exists, the same math that detected gravitational waves, and now you can also use it on your own telescope images. If the video sparked your interest, you can subscribe so others can see it too. And see you next time. Until then, measure carefully, stack patiently, and trust the math.